Hi everyone. This handout project is titled Spectrophotometry Modeling of Galaxy. This goal is to test the contribution of stellar dust gas on the spectral energy distribution, and is with the sample of nearby galaxy. And this project was developed by Barnaby, Deb, Achia, Alessandro, Jim, and me, Anna, and was supervised by Daniel Dale, Yannick, and Patrice. Yeah, the sample is a subsample of kin fit. This subsample contains 33 galaxies of the nearby galaxy, and they are at distance less than 33 megaparsec. And for each galaxy, we have 23 photometry observation in the large wavelength range from UV to from far infrared. And this galaxy covered different type of galaxy like spiral, intermediate, barred, and irregular.
So for these 33 galaxies, we have a large coverage of the spectrum that gives us a spectral energy distribution of them. And for each for emission at each wavelength, they correspond to different physical processes. For the stars, they emit from the UV to far infrared, and then the high energy photons will ionize the gas that contribute to the emission lines and also some continuum. For the dust, that will absorb some photons and re-emit in the infrared range. So for our work, we would like to fit using models to reproduce our spectral energy distribution. How are we going to do that? Okay, luckily we have a seagull, which fits perfectly our location of summer school, South France, and also our summer without air conditioner. Okay, I'm kidding. So for seagull, it's a Python code that investigating the galaxy emission. It includes the model of the star formation history, single stellar population models, nebula emission, continuum dust attenuation emissions. But in our model, we didn't include the aging emission X-ray redshift because they are nearby galaxies and also no absorption of the IgM. The bonus is like for seagull, it includes the energy balance between the stellar and dust emission.
So first, we started by using only the photometric data to fit the spectral energy distribution of our 33 galaxies. So here you have a histogram of the reduced chi-square value for our fits. You can see that for most of our fits, they are close. The chi-square value is reduced. Chi-square value is close to 1, except for 2 galaxies which have a chi-square value of 44.5, which is not great but not terrible. That's it. And here you have an example of the fit that we have done for NGC 5457. You can see in blue the model spectrum, and you can see that it fits quite well the observed flux, which are in white dot, and you can see that the chi-square value is is optimal for that case.
So the fitting here, we first do the fitting using just photometry. And so using the fits, only photometry, using the ACD fits from just photometry, we can derive physical parameters for each of our targets. And so we were trying to reproduce the stellar mass star formation rate relation. And when we do so, we find a pretty good correlation with observations, with a few exceptions. So the Peng et al. 2010 line is from observations in blue, and the data points are one for each of our targets. But we noticed that there's a dwarf galaxy in our sample, which really stretches the Peng 2010 relations down. beyond where it should be valid. We also find two quenched or early type galaxies in our sample, which are not expected to follow the star forming main sequence. And so once we clean up our sample, we see things line up better with observations, but we still see a few problems since we're only using photometry. And it seems like we're underestimating the star formation rate in a lot of cases. And the problem with using just photometry becomes even more obvious when we try to predict line ratios, since we're not feeding in any line emission information right now. And so we try to make the BPT diagram. So on the BPT diagram, moving from left to right on the x-axis, you're basically increasing the metallicity, and like bottom to top, it's increasing gas excitation. And it's supposed to tell you whether a galaxy is star forming or has an AGN. And when we do that, we see that a lot of our targets, although having very different star formation histories, sort of fall on top of one another. And that's mostly because we're using the predicted line fluxes without giving any line information to begin with, which is not something that people generally do, but we're just trying things out. And this is expected since line fluxes actually depend on nebular parameters, such as the ionization parameter, the gas metallicity, and electron number density, which are parameters that we've played with without actually giving any line information.
So the previous results, like as Deb was saying, were plotted only using the photometric properties. So we decided to give in line intensities as well. And we do so using the Mustakas et al. Sample. And here we don't have like one line intensity per galaxy it's not a global line intensity. We are looking at, the sample looks at 3 spatial locations, which is basically the nuclear, the subcircumnuclear, and rectangular radius strip. So we input the H alpha, O3, H beta into line intensity ratios. And now let's look at how that affects the results of our SED. So on the left, we have the histogram of the reduced chi-square. And as you can see, this is much higher than what we had before. Before, we could constrain it better in some sense because all the values were less than 5, but now it's up to 40. And that's what we expect because we're giving a very tight constraint by just giving one value per line intensity, and you're asking SIGAL to constrain it. That makes no sense. So it becomes very difficult. And on the right, we just have a fitting for the same galaxy as we showed before. And one more thing that we wanted to point out was that the reduced chi-square in the nuclear region has a much greater spread because the nuclear region is like a very small part of the galaxy and not the entire galaxy. So that's why we see the spread in the yellow part of the reduced chi-square.
So after adding the information on the measured line intensities, we wanted to have another look at the 2 plots that we showed earlier. So starting from the stellar mass to star formation rate plot, here the only significant change is that our points shifted a little bit up, looks like it. I mean, the mean scatter is more or less the same, but it looks like there's not that bias in underestimating the star formation rate as we were witnessing earlier. But yeah, the points are better centered around our reference relation. It's also an exercise worth a look to try and plot the ratios between the predicted line fluxes without normally we would do this with the observed ones, but we wanted to have a look also at the predicted output by SIGAL and plot them in the BPT diagram again, this time using the line fluxes information. And what we see is that we have a higher spread of points, so we are better covering the space of parameters now that we are adding this piece of spectroscopic information. And as we look at the difference between the 3 components, we actually see them populate in the same region. We were not expecting that. We were thinking that different components would have populated slightly different regions of this diagram, but we must keep in mind that we're still using just 4 lines comparing to 23 filters. So the photometric information is still the dominant one.
So on this project, we learn 4 main points about SIGAL. So first, SIGAL is a versatile tool for fitting SEDs of galaxy and estimating their physical properties. But you need to be careful on 3 points. First, the goodness of it is sensitive to the choice of model and of the grade of parameter you use. And then you must be careful of really 2 points, you can say. So first, it's possible to estimate physical properties using only photometry, but then it's difficult to predict emission line fluxes. So you can try to solve that using by adding measured line intensity to the fit. But then the chi-square is increase, inflate. So you have to be conscious of that. So on the picture, you have a representation of us building of us all when we are trying to build a model with SIGAL. And to conclude, that was us when we were running SIGAL, and we can see that the laptop was overheating. So maybe SIGAL may cause global warming. So yes, thank you.
Well, on that fiery moment, do we have questions for group 4?
I was wondering about those 2 outlier galaxies at the start. If you know was it something about the galaxy properties of the SEDs that made them hard to fit with respect to chi-squared?
Are you talking about the 2 that were like sort of at the bottom? Like those 2?
When you were showing the chi-squared.
Mm-hmm. Yeah. So our SIGAL, like SED fits, since we have such a large range in galaxy properties for targets, it's very sensitive to what parameter ranges we put in. But specifically for those 2 galaxies, we were underestimating the UV flux. And we tried to sort of counter that by changing our star formation history model. So we were using a delayed star for, what was it? Yeah, just a simple delayed star formation history, but then we changed to a delayed star formation burst quench model that kind of like brought the chi-square down a lot. And so those 2 are like outliers that we're still having a hard time fitting the UV.
Other questions? Well, I might steal from Jerome. So with the 2 chi-squareds, the early type galaxies with the quenched history, that were for the high chi-squared objects, right?
Yeah.
Yeah. Okay.
So do you have a physical explanations for the galaxies that does not lie on the relationships? Did you discover a new category of galaxy?
You mean it's stellar mass versus star formation rate? No, actually, we were unsure about the lack of star formation rate. The only thing we could think of is connected to what you said. So we weren't able to properly model the UV part, and even with the new model, where we do have the higher reduced chi-squares is always due to that part of the fit, which went didn't come up so well. So I think it's just a fitting issue. Yeah.
All right. Any last questions while group 1 comes down? If not, let's thank group 4.